Now we come to Lecture 6 of Unit 1. Specific work. Specific work is the work per unit weight. Work per unit weight. Specific work in turbo machines such as fans, pumps, compressors, or turbines has the SI units Newton, meter per kg, or where there is heat, joules per kg, or where there is distance and speed, it's meter square per second square. Specific work of pump or a fan working with an incompressible fluid can be expressed as work. Specific work is equal to P2 final pressure minus initial pressure divided by rho, where P is the pressure in Newton meters, Newton per meter square, and the rho is density, kg per meter cube. So in a pump and fan, the final pressure is always more than the initial pressure. It's the other way in respect of turbines. The specific work of turbine, here the initial pressure is more and it gradually tapers off during the cycle. So specific weight of turbine with incompressible fluid can be expressed as work is equal to P1 minus P2 divided by rho. Specific work of a compressor with compressible fluid. In these two cases, it was incompressible fluid, and the work of a compressor is to compress the fluid, whatever is inside. With compressible fluid, and specific work for isentropic compressor can be expressed as P1 V1 by rate part K to P2 V2. V is volume, P is pressure, K. K is the ratio of specific heats, joules per kg Kelvin. Same expression is for gas turbines expanding in a compressible fluid. The same is applicable for a gas turbine. Same is there. Specific weight is defined as that specific work. Now we come to specific weight. Specific weight is defined as weight per unit volume. Weight per unit volume. Weight is a force, and we know that the SI unit is Newton per meter cube. The specific weight or force per unit volume can be expressed as gamma is equal to rho Ag. Rho is specific weight, as we have said, Newton per meter cube. Rho is density, and Ag is the acceleration due to acceleration of gravity, 9.81 meters per second square. Now, specific weight of some common materials, there you will get an idea. In kilonewton meter cube. Aluminium, it is 27. Brass, 84.5. Gasoline, there is petrol, 6.67. Mercury, 133.7. Mercury, that's why it's considered very heavy. It's a metal, considered metal. Mercury. SAE20 motor oil, which we put in our scooters and cars, 8.95. Water, 9.81. Seawater, because of salinity, salt, 10.03. And for stainless steel, it is the order of 78 to 80. Having seen specific work and specific weight, let us come to the work ratio as per your syllabus. In Carnot cycle as we know, so many times we have discussed, is the most efficient cycle. In a Carnot cycle, it is defined as the ratio of net work to gross power output. Gross power output is Wg, net work is W. The expression will be work ratio will be W by Wg. Net work divided by the gross power output. Has a low work ratio, this Carnot cycle, though most efficient for power generation. For power generation, I think we had covered in the earlier lectures. It is very efficient and therefore it was used for power generation. So theoretically, it can't be used in practice. Only for power generation. Work ratio of a gas turbine, work ratio of a gas turbine is defined as the ratio of net work output and work done by the turbine. Ratio of net work output and work done by the turbine. There is something known as back work ratio also. Some of the power produced in a turbine is used to drive the compressor. Some of the power produced in a turbine is used to drive the compressor. The ratio of compressor work to turbine work is back work ratio. Just to give you an idea. Now to come to mean, what is mean effective pressure? MEP of an engine. It is the average. Now average is important because the pressure varies, as you know, in a four stroke. Pressures are in the cylinder are different in different strokes and it varies from almost zero to very high. Is the average pressure in the cylinder for one cylinder for a complete engine cycle. By definition, it is the ratio, MEP is the ratio between work and engine displacement. So we have an expression PME, power ME is equal to W by VD, where as I said, PME in pascals is the mean effective pressure, work in joules, work performed in a heat engine, joules, in a complete engine cycle, and VD is the engine displacement, VD volume, D volume, engine displacement in meter cube, engine cylinder displacement. So let's keep note that this is 1. Equation 1, PME is equal to W by VD. We will use it in the next page. So PME is equal to W by VD. This is the equation 1. We can write the expression of the engine work as W is equal to PME into VD. We have just changed the equation. This we call it equation 2. Now, there is also a direct relationship between the power of the engine and work produced. Work produces nothing but nRP by NE. nR is number of the crankshaft rotations for a complete engine cycle. Therefore, for 4-stroke it will be 2 and 2-stroke it will be 1. P is the engine power or NE is the engine speed, revolutions per second, engine speed. So, by making equation 2 equal to 3, we get the expression of the mean effective pressure as a function of pressure, power and engine speed. That is PME is equal to, we replace W by this nRP by NE divided by VD. This we call it expression 4. Now power is the product between torque and speed. We know that. If omega is the speed, power is equal to speed into torque. Omega is nothing but 2 pi NE. 2 pi NE, engine speed, 2 pi into torque. This is 5. So by replacing 5 in 4, we get the expression of mean effective pressure as a function of as PME, 5 in 4, PME is equal to, we have replaced this power pi NET, 2 pi NET divided by VE, VD divided by VD. Any cancels. One on the above and one below. They cancel out and you get PME equal to 2 pi nRT divided by VD. Here. We call this equation 6. Now from equation 6 we see that the mean effective pressure is not influenced by the engine speed. We have cancelled any. So engine speed has MEP is not influenced by the engine speed at all. It's quite apparent from this equation. Secondly, since torque is divided by the engine capacity, if there are 4 cylinders, it will be divided by 4. The MEP can be used to compare IC engines of different displacements. If NC is the number of cylinders in an engine, then the expression becomes PME 2 pi nRT VD and divided by NC. There, number of cylinders is there 4, NC will be 4. Maruti 800 3, this will be 3. So what is this used for, this expression? MEP is used for initial engine design. When the engine designer, the factory is designed, this PME, MEP, mean effective pressure is used for engine design calculations with engine torque and MEP as inputs. Torque and MEP is known, and then we can 2 pi reasons, then we can calculate VD. VD is nothing but the engine displacement, and we can calculate the volume of the cylinder. From the volume, we can calculate the diameter and the stroke. VDC to TDC. So we can calculate. This is how a designer engine is designed. This is the higher stuff, but you should know. Remember that point to remember is that MEP is only a parameter to judge engine performance and does not reflect the actual pressures inside an individual combustion chamber. It is only a parameter for design purposes. It does not reflect the actual pressures. On some basis, the design has to be made. Now there are different types of mean effective pressures. Indicated mean effective pressure, IMEP, brake mean effective pressure, BMEP, friction mean effective pressure, FMEP. What are each? What are they? Indicated mean effective pressure is the mean effective pressure calculated with indicated power. Indicated power in an indicator diagram. We know that the power is, when you draw a PV diagram, the area inside the curve is the work. This parameter does not take into account the efficiency of the engine. Brake mean effective pressure, this takes into account the efficiency. The brake mean effective pressure is the mean effective pressure calculated from the dynamometer power to torque. The crankshaft, end of the crankshaft, you can calculate it by having a brake system. This is how is it calculated in the lab. This is the actual output of the internal combustion engine at the crankshaft. crankshaft output before it goes into, before the flywheel, before it goes into the clutch and gearbox. So brake mean effective takes into account the engine efficiency. So this is just indicated. This is the actual. Think it that way. Frictional mean effective pressure is an indicator of the mean effective pressure of the engine lost through friction. Mean effective pressure of the engine lost through friction. There are frictional losses. There is a piston moving up and down. There are other components moving. And it is the difference between indicated mean effective pressure and brake mean effective pressure. Indicated is always higher. The indicator diagram will be higher. So F MEP is equal to I MEP minus B MEP. If we know the frictional mean effective pressure from equation 7, this is equation. From equation 7, if we know, we can calculate the frictional torque TF as PME multiplied by this divided by this. Start with this into this divided by this torque, frictional torque. If we consider the mechanical efficiency of the engine, mechanical efficiency NM, we can write the brake mean effective pressure function of the indicated mean effective pressure. That is, BMEP is equal to mechanical efficiency into indicated mean effective pressure. So this is the calculative level, and this is the efficiency into IMEP will be equal to BMEP. And from this we can derive the expression NM is equal to BME, NM is equal to BMEP divided by IMEP. BMEP is nothing but IMEP minus NEP, FMEP divided by IMEP. We have got this into this. So I will cancel 1 minus FMEP divided by IMEP. This is the mechanical efficiency of an engine. You can calculate this. This lecture finishes, and the next lecture we will see as per the syllabus. Thank you.